Welcome to the energy transfers marking video. Question 1. An electric fan powered using a battery is used to move air around a room. Straight away when I see battery I should be thinking chemical energy store, and I should be thinking fan, blades moving, kinetic energy store rather. The question is to describe the energy transfers that take place. Now whenever you're describing energy transfers, it hasn't specified which type, so you could talk about useful and wasted, and we should also, as the hint suggests, talk about the store, the object, and the mechanism of energy transfer. So the first mark is for saying the battery's chemical energy store decreases, and the second mark is for saying that the energy is transferred electrically, that is the mechanism, to the fan's kinetic energy store. So we've talked about the new store in which there is now energy. There is also a mark available if you didn't get one of the other marks for saying some energy is transferred to the thermal energy store of the surroundings. That mark generally is available for nearly all energy transfer questions, so it's worth remembering that, and there is another phrase which we'll come to later on in the video. Question 1b. Because this question talks about all of the energy from the fan is eventually transferred to the particles that form the surroundings, whenever we talk about energy of particles, we refer to internal energy. So this increases the internal energy store of the surroundings. 2. The diagram shows a climber partway up a cliff. Complete the sentence. When the climber moves up the cliff, the climber increases the energy in their gravitational potential energy store. We know that because the higher an object or a person is, the more energy they have in the gravitational potential energy store. It's linked with height. Now, we are told that in the question the height climbed is a total of 20 meters, so immediately I've labelled that height or distance. Either is fine for now. The question is asking us to calculate the work done that the climber must do against gravity to climb to the top of the cliff. We are told the weight, which is the force, because it's measured in newtons, is 860 newtons. So, if I follow the method, I know force, I know the weight, I know the force, which is the weight, 860 newtons. I'm trying to work out what the work done is, and I know that the distance climbed is 20 meters. So I know my formula is work done equals force times distance. I substitute and I get my final answer, which is 17,200 joules of energy. Question 2bi. It takes the climber 35 minutes to climb to the top of the cliff, so I'm going to label that with a T. During this time, the energy transferred to the climber equals the work done by the climber. So I know energy transferred is E, but it's telling me this is the same thing as the work done. And we know that energy transferred is just a synonym for work done. We're told to calculate the power of the climber during the climb. So I need to calculate P, and I know work done, and I know T, and that should tell you what formula you should be using. So the time is 35 minutes. The energy transferred to the work done I know from the previous question, which is 17,200 joules, and I know the power is measured in watts. So I write the formula, substitute, and get my answer to three significant figures, which is 8.19 watts. Now you might be asking, how do you know what value of energy transferred or work done to use? Well, we know that from the previous question, the work done against gravity was 17,200 joules, and the big clue here is the energy transferred is equal to the work done by the climber. So you need to always, whenever there's a part of a question, to look back at previous parts, because they will usually be connected. Question 3. A car accelerates from a set of traffic lights. The driving force of one back tyre on the ground is 3,000 newtons. How much work is done by the force of the two back tyres when the, I should say driver really, because it's not a cyclist, it's a driver, travels 10 meters? So, we are given the force of one tyre, but we're asked to calculate the work done for 2 tyres. So there is a little trick in this calculation that will need to be performed. So here's what we do. We know the force for one tyre is 3,000 newtons, but we're asked to calculate the force. We're asked to consider the force of both tyres because we need the work done on both tyres. So it's doubled to 6,000 newtons. 3,000 times 2 is 6,000. We need to work out what the work done is, and we know the distance that the cyclist travels is 10 meters. So I'm using the formula work done equals force times distance, and I get an answer of 60,000 joules. The next question says, what happens to the energy transferred by the forces? Well, we know that if you've got a cyclist, keep thinking it's a cyclist as a car, we know that most energy increases the kinetic energy store of the car, but that some energy will be dissipated into the surroundings, and it's good to specify how. It's usually as heat, although with a car you can also get sound. Instead of saying that for the second mark, you could say energy is used to overcome friction or air resistance, but it's always a safe bet to talk about this because this applies to pretty much every single energy transfer. Some energy is always wasted, or the technical term dissipated, to the surroundings. The next question is very similar. It's about a torch, and we know it's battery operated, so again, what should you label all batteries with? Because you know what energy store it is. It says the torch's battery contains a store of energy. Describe how different stores of energy change when the torch is turned on. So, energy in the battery's chemical energy store decreases, and we know that because as the light remains on, the chemical energy store will go down because that energy is being transferred from the battery. We know that energy is transferred usefully as light waves, so that is the energy transfer taking place. Now remember, you can always say thermal energy store of the surroundings increases because that always happens as well. Next we have a calculation question. If the torch is thrown at a speed of 6 meters per second, so I know that's going to be my velocity, and has a mass of 700 grams, and remember, in physics, grams is not the standard unit for mass, it is kilograms, whereas in chemistry it's usually grams. So I'm aware I need to convert this before I even know which formula I'm expected to use. Calculate the kinetic energy of the torch. So again, we list the values that we know, we convert the mass, we write the formula, substitute, and our final answer should be 12.6 joules. The next question asks us to explain why having low resistance wires will improve the efficiency of the torch. Now remember, see if you can remember what efficiency equals as a formula. It is useful output divided by total input, and therefore it's a proportion. So it's important in this question, or you will be awarded marks for talking about proportions. So the first thing is, low resistance wires means less energy is wasted. Remember, this is one of the ways we can make something more efficient, is by using low resistance wires. So less energy is wasted, or in other words, there's a lower proportion of wasted energy. And the second mark is for saying that more energy, or a higher proportion, is transferred usefully, but you have to specify why that is the case for the torch, and that is because the energy transferred as light, or you can say radiation. Okay, next question, question 5. Now this is quite a tricky question, so I suspect lots of us will have got this one wrong, so pay careful attention. The diagram shows a motorbike of mass 400 kilograms, straight away I put M there, being ridden along a straight road. The rider sees a traffic queue ahead. He applies the brakes and reduces the speed of the motorbike from 20 to 4 meters per second. Now, we are asked to calculate the kinetic energy lost by the motorbike. In other words, we need to first work out the kinetic energy store when he's going at 20 meters per second, then do the calculation again for 4 meters per second and subtract them. find the difference between the kinetic energy store after having calculated it. Now some of you might have done 20 take away 4 and used 16 as your value for velocity, but that would be incorrect. If you do those calculations in those two methods, you would find you get different answers. So here is the correct answer. First, we use the formula because we know we've got mass, velocity, and we need to find kinetic energy. We know we need to use the kinetic energy formula, so once you do your substitutions, you find you have 80,000 joules when we use 20 meters per second. When you use 4 meters per second as your velocity, you get 3,200 joules, and then we need to subtract 3,200 from 80,000 to get 76,800. That's the amount of kinetic energy lost as the motorcyclist brakes. The next question is saying how much work is done on the motorbike by the braking force, and it's going to be the same as the kinetic energy lost, because that is the amount of energy transferred during braking. What happens to the kinetic energy lost by the motorbike? Well, we know that if the energy is lost when you're braking, you must be increasing the thermal energy store of the surroundings. Now, I said earlier in the video I would give you another phrase instead of this that you could use, and the other phrase is this. The internal energy store of the particles that form the surroundings increases, dissipation. If you learn that, and you learn that, and you use any one of those, whenever there's a question about energy transfers, it's very likely that you'll get a mark for saying that, as you'd have noticed in the exam questions we've done so far. Final question, again quite a tricky question. We've got a pole vaulter, which is this type of sport, a bit like the high jump, but using this pole to get over a bar. In order to jump over the bar, the pole vaulter must raise his mass by 5.25 meters. So he needs to get up to 5.25 meters. The high jumper has a mass of 75 kilograms. Notice I'm writing down H or D because it could be height or distance. In my formula, mass is 75, G is gravitational field strength. So I'm already thinking which formula has mass, gravitational field strength, maybe height or distance, and then it tells me calculate the gain in gravitational potential energy. So I know straight away this is what my formula is, but I'm going to list my values first that I know. I'm trying to work out the number of joules of energy for the gravitational potential energy, and I should find my answer is 3,860 to 3 significant figures. Of course, this is the correct answer as well. It does not specify how many significant figures, so this is correct, this is correct. If you said 3589, that would also be correct. And then finally, it tells us to calculate the minimum speed that the pole vaulter must reach for the takeoff in order to get over the bar. Now here, what that means is, if we want to work out speed, we need to basically find the value for v. We need to find the velocity needed. Now, velocity we know is linked. We don't really have any other information, and we know that the energy is something we have worked out. So the only other information really we have is the height, the mass, gravitational field strength, and the gravitational potential energy gained. Now that is important because whenever a pole vaulter jumps, there's always a transfer of energy. But before they jump and energy is transferred into the gravitational potential energy store, they're doing a run-up before that. And in that run-up, the kinetic energy that they have is then transferred into gravitational potential energy when they jump. So we do know how much kinetic energy they must have had, because it's the same as the potential energy, which is 3,858.75 joules. And now that we have understood the link between the EK and V, we know their mass. That's the formula we need to use. Substitute and find that v squared is 102.9, so v would be the square root of 102.9, and we should get 10.1 meters per second to 3 significant figures. This is quite a tricky question and is most likely to appear in the higher tier paper.